So let's talk about embodied design for spatial geometry learning. This talk is based on some very recent conference papers. Some of them are written with Professor Dor Abrahamson and his team, and some with my graduate students. Okay, and also one of the journal papers is recently published just now in For the Learning of Mathematics. And okay, this is, so you can see this, yes? And then my student asked me, do the boxes really exist? So it's a strange question, yes? We all know boxes. Probably we have dozens of them in each of our houses. So it's a strange question to receive. And so I read this question as a citation from a reflection of the pre-service teacher assignment. And and this is even more strange because, okay, so this is explained like this. So in the Hebrew word for cuboid or rectangular parallelepiped is teva, and the same word teva we use for box. So actually, this student was not asking, does boxes exist? She was asking, is this mathematical object really exist? But also, it is still a very strange question because it is the same word for box. And also, it's not an unusual word. It's not like I'm talking about icosahedron or something like this. So it's also part of Hebrew language. And so for instance, it's part of expressions like box for letters, a postmail box, or for instance, if we are talking about treasure chest, it's also contains the word box. So okay, so it was very strange, but it was connected to, it was in context of spatial geometry. And spatial geometry is very hard for students in Israel. We know that in general, Israel students are not very good in geometry questions, for instance, in international exams. We also know that they are trying, even teachers, when they are teaching, they're trying to avoid geometry, and they also try to avoid spatial geometry. Okay, but this is not unique for Israel. For instance, this is a question which Fujita and colleagues asked in their test. And they asked this question, as you can see, thousands of Japanese students. So as you can see in the cube, can you identify the shape ABC? So which kind of triangle is this? And you can see that in grade 4, only 12 and 6 point students answered correctly. And in grade 9, a little less than 50%, than half of students answered correctly this question. Okay, so this is question in spatial geometry, and this is hard for students. So spatial geometry in schools, students are struggling with spatial geometry tasks. We can see this in work of Fujita, but this is only one explanation. Students are required to visualize three-dimensional objects given two-dimensional drawings, okay? And as Weider and colleagues in 2019 showed that there is some objective challenges in two-dimensional representation of three-dimensional figures. By the way, this is a fascinating article of Weider. I suggest reading this. So, are we giving them all the tools for success? This is what the question that I'm asking. So, spatial geometry demands it's a combination of spatial vision and geometric knowledge. There is not much knowledge about the processes of solving tasks in 3D. Mittal and Balachev in their recent papers, they continued Duval from working with figures to the perception of geometric properties. So this process, when students have to do, when they perceive some figure, and from this continue to perception of geometric properties, is also relatively very little studied. Okay, I also want to show you some historical problem, a philosophical maybe problem, which is called Molyneux problem, and this is also to set up the scene. So William Molyneux initially presented this question to John Locke, famous philosopher. So Locke interposed this question into his famous book, An Essay Concerning Human Understanding. So actually, Molyneux asked a very simple question. If we have a blind man who learned about geometric bodies just by sight, and then somehow this man received his vision back, and then we will show him or her these geometric bodies, not difficult geometric bodies, but a cube and a sphere from the same material. So will it be possible for this man who just received his vision to understand which is which, where is, just by sight, without using the sense that helped him or her to understand and to receive information before? Okay, so Locke and Molyneux, they answered this question negatively. The blind man at first sight would not be able with certainty to say which was the globe, the sphere, and which was the cube, whilst he only saw them. And both Molyneux and Locke suggested then when this man will start exploring these shapes, both by sight and by touch, then it will be possible for her or him to understand what is happening, what is the sphere and what is the cube. And what is interesting is that in 2011, amazing study was conducted because now we are able to make people who were blind to see. And so psychologists and neuroscientists jumped on this opportunity and gave exactly this. And as you can see from the results, so first of all, these persons were not able to understand which is sight, only by sight, which is cube or which is sphere, and other different. But then when they started to explore this by using two senses and combining experience from two senses, then it was possible, and even when their vision was not so good, because it's a process, as you know. So I'm asking this question: does our way of teaching, in particular geometry and spatial geometry, make students kinesthetically and tactile blind? And how we can change this? Okay, so my theoretical perspective is a perspective of embodiment. So embodied term in cognitive sciences is that perception and action, it's a statement and claim that perception and action are formatively constitutive of our thinking cognition is modal and situated activity. For instance, Camero is talking about this. And also, additional postulate from embodied cognition. The mind's function is not to represent the environment precisely, but to engage with it dynamically vis-a-vis social biological task demands and emergent contextual contingencies. So this is a second claim of embodied cognition. And then environment offers opportunities for potential action, affordances, as saying ecological psychology following Gibson, that the agent interactively discerns and incorporates. And when we engage with the world with fellow humans, we coordinate with them perceptual orientation in relation to shared situations. So here I should have cited the work of Goodwin. So, and these are mostly, so we have some evidences from cognitive science and from neuropsychology that we're starting to accumulate that, so our thinking should be and is influenced by our body, by movement and by action. So when this evidence from embodied cognition started to appear, then learning sciences started to be interested in this. And so what are foundations for design principles which are common for environments which I design and study? So first of all, I'm talking about embodied learning. First one, as I just cited, distributed cognition. So we have a reflective conversation with material when we are working, for instance, with different materials, when we're constructing something, where rearrangement of material objects support problem solving. And also embodied design for mathematics education. So Abrahamson and colleagues, they stated that conceptual learning could emanate from or can be triggered by experiences of enacting or witnessing conceptually oriented movement forms. And only then formalization of these gestures and actions in disciplinary formats and language. So for instance, if in work of Abrahamson, first students enact something, for instance, they enact some movement of hands on touch display, then they can discuss these new acquired forms of movement and ground into them concept of proportion and proportional thinking. This is one of the most famous examples. Another foundations for my designs can be found in Pappert's constructionism. So Pappert was famous for his fight with paper math. He is taking this into realm of computers and use of technology in education. However, I perceive this postulates of constructionism more widely. So learning through making with an emphasis on learners' interactions with their artifacts, not just programs and not just robots, but also for something that they just build with their hands. And also the critical role of cultural surroundings. I already mentioned Gibson's ecological psychology, that environment offers opportunities for potential action, affordances, then the agent interactively discerns and incorporates. And finally, there is a rich tradition in mathematics education of work with tools and special machines and models. For instance, Leonardo da Vinci and Felix Klein, and also worked with this. And for instance, there is a famous citation of Klein. A model, whether it be executed and looked at or only vividly presented, is not a means for this geometry, but the thing itself. Okay, I find this very inspiring. So the activities which I study and which I will present findings about have several common features. It's all spatial geometry tasks. Students in them generate and transform material artifacts. First, they construct them, and then they answer questions about mathematical properties. Then, it is also collaborative problem solving, because you will see that in all three experiments, they are working together. The models are on different scales. So, for instance, we can work with something which looks like this, okay, something which I can hold in my hand. But also, as you will see, we can work with something which is much bigger, like human-sized models. I will explain it a little bit later. And the instruction which I'm giving them, so this semantic, semiotic means, contains text and two-dimensional diagrams. So they are not provided already with 3D dimensional model, okay? They have to construct it mostly by textual and two-dimensional instruction, okay? So my research questions, which are I'm trying to answer in this work: how students ground geometry concepts in action-oriented perception. Which role students' multimodal action-based interaction with concrete material plays when students solve spatial geometry tasks. When students study 3D geometrical objects by exploring physical models, which shifts of attention do they experience? And what role do physical features of the models, for instance, their relative size and their orientation in space, play in the process of students' exploration? So I mentioned shift of attention in my third question, so it will be a little bit more theory about it, but I think that this is important. So Mason, in his works, he is saying that for him, learning constitutes shifts in form and forms of attention. Transformation of attention involving shifts in the form as well in the focus of attention. And he postulated also that there are 5 structures of attention, 5 forms. First of all, one may hold the wholes without focusing on particularities. One may discern details among the rest of the elements of the attended object. Okay? So, for instance, I can look on the icosahedron, yes, as a whole. I can discern some details. For instance, I can focus my attention only on vertices, or maybe on some group of edges, okay? One may recognize relationship between discerned elements. For instance, I can say, wow, 3 edges form exactly one face, okay, for instance. Also, I can perceive properties. I can say, okay, well, I can see that exactly 5 are coming from the vertex. Let's check what will happen in another one. So here I'm not just recognizing relationships. I am perceiving this property. I'm conjecturing and think, okay, yes, here it's also 5. And then finally, I can reasoning based on perceived properties. For instance, I can find some formula or some way to calculate how many edges are here, or how many faces, or how many vertices are here. Okay. So, but as Mason is saying, and this is exactly correct, as we know, we can jump between them, and sometimes we come back, for instance, to hold the whole and to reassess the situation. Okay, so I will start with the first example. Outdoor implementation of the activity, group of 6th, 10th grade students, semi-formal part of an enrichment program. Okay? So I'm skipping this. Okay, so there will be 3 teaching experiments. First, students' experiences with 3D pen, sketching while solving special geometry problem. And there will be 3 10th grade students faced with a task for approximately 20 minutes. Third experiment will be students' experiences of construction and exploration of human scale models of 3D solids. They will try to construct the model and work on several questions about geometric properties. And third, students' experiences of construction and exploration of human scale and handheld models of 3D solids. Okay, so there they will have, okay, so let's see which I will show you first. Just a minute. Let's go, maybe I will show you, just a second. Okay, because I just a little bit rearranged the. Okay, I will start with different with this one. Okay, so can you see the slide with the cubes?
Yes.
Okay, so that will be better. So this is a teaching experiment, as I said, so you can recognize this is very similar to the question of Fujita, okay? So we have here a cube and 3 diagonals, and then I gave students this 3D model, something like this, okay? So they have a cube, just the cube, and then they have this 2-dimensional diagram, and they have some questions. So they have to answer true and false questions and explain your reasoning. So first, I'm asking, is this C, B tag, D tag? Okay, so is this angle is right angle triangle? Then I'm asking, is B tag, D tag, is the shortest side of this triangle? Then I'm asking, maybe this triangle has an obtuse angle. And finally, I'm asking, is it true that in triangle C tag, C, B tag, D tag, all angles are equal? So these guys, they constructed this what they constructed. So they constructed this with 3D pen, and this with 3D pen, and this with 3D pen. And for you who don't know, maybe, so this is the device, and this is device which is very, very simple device, very cheap device. It extrudes thermoplastic, and it takes its form immediately. Okay, so it's so they practiced with this, and they produced this. So here you can see, sorry, how this was constructed. You can see also some model which they constructed before to train their skills. So they constructed a pyramid. Okay. And just to show you how this process is coming. So this is another task, but you can see just what is happening. Okay, so this is how they sketch. Okay, and now I'm showing you their utterances, their conversation. So one of them is saying, you know, this is a cube, and this cube face is a square, and then this is 90 degrees, then this is 90 degrees, and then diagonal bisect the angle, so it is 45 degrees. And another student asking the question is, if we rotate two faces, would it be the same angle? Could it be? To them, the angle in the picture also looks like that 90 degrees. In the picture, it is just from a different angle. If you turn it like this, you can see that this, it points, is the right angle, and this is stretched. So, as you can say, when I designed this experiment, I thought that when they will draw the diagonals of a cube, and if they will have this model with drawn diagonals, the solution will be immediate. However, it was not immediate, as you can see, and these are students that are starting to learn in the 10th grade. They are very strong mathematically very strong students. They received very good training, and now they are in relatively strong, yes, you can say this very strong school. So, and it is a problem even with a model. So, what was also interesting, then when they completed this 3D drawing, the students made inferences and conjectures about tasks without taking the model in hand, only lightly touching it and making minor adjustments. And most of these adjustments reoriented the 3D model vis-a-vis the given 2D diagram. So they tried to make the cube, the actual model of a cube, three-dimensional model, to look like a two-dimensional diagram. And they all even interacted with it just by tilting the head. You can see this. Can you see this girl from the right? So she's not taking the cube and starting to turn it. She just tilting the whole body. But what happened? It was a breakthrough. So the boy there, he was unsatisfied with the claim that this triangle, which of course we know that this is equilateral triangle, okay? He was not satisfied with this answer that they gave as a group, that this is right angle triangle. So he's saying, if these two angles look like the same shape, okay? So he's taking this perspective of another person. If they are both right angles and triangle has a total of 180 degrees, then the triangle cannot exist. This is impossible. If you rotate it each way to make it one of the angles look like a right angle, then you can rotate it in a different way to make other angle look like a right angle. You can see that at this point, they are not touching the model, but they're starting to speak about it using the word rotation. This is a very strong argument for him. Then, what is happening, then the second girl, finally, after 7 minutes of work, she took this into her hand and started to rotate it. Okay? And she rotated for 5 seconds, and then she said, now I get it. But she is not getting that this is equilateral triangle. She's just getting that the argument of the boy. So she tried to formulate her vision, and the core of her argument was in line with this that was said. So from different angles, the triangle appears as isosceles, and yet its angle cannot be. But during this minute of work, boy's attention, G's attention, was on the rotating model, enabling him to see it under these transformations, under these rotations. In contrast, Another girl, she was sitting there and she was ignoring totally rotation of the cube. She was focused on the 2D diagram and she tried several times to draw her peers' attention to it. She just said, look at the picture. She almost said, like, forget about the cube. Just focus on what we have. And then you can see this, how the idea and how the right correct solution is born. So it was born from some tentative ideas, and then it was solidified in the form of rotation, by rotation, through rotation of the model. So you think all the angles are 60 degrees? Is it equilateral triangle? And his argument, yeah, look, all the sides are of the same length. And he traces with finger, okay? So he is accompanying this with gesture. Look, all the sides are exactly a diagonal, the diagonal of a square. All the squares are the same. And that means if all the sides are equal, all the angles are equal, and they are all 60 degrees. And then it receives, actually, it receives the confirmation of the whole group. So, from my perspective, the findings are of this teaching experiment. First of all, the task demanded that students harmonize their spatial reasoning skills with domain-specific knowledge of planar geometry. We can compare it with findings of Fujita. Coordination of traditional and novel medium, traditional as paper and novel as 3D cube with drawn auxiliary lines, yes, is not easy for students. They cannot take this for granted. 3D drawing per se was not enough for the solution. Even given a model and after actually drawing the problem, the solution was not straightforward. Students tentatively experimented with their new degrees of model freedom, looking at objects, pointing at them, touching them, lifting and rotating them. So these actions and these gesticulations were not just, something that kids do. No, it was actual part of their solution. They built their reasoning on this and then were able to combine to connect with their actions, their knowledge of geometry. As you can see, they knew the properties of square, they knew the properties of cube, they knew how they, if the squares are congruent, then diagonals are equal. So, and they also knew the properties of equilateral triangle. But they were able to rise and to evoke this knowledge just only by actually acting. Rotation of the model combined with geometric conjecture led to the collaborative breakthrough. In tasks combining 2D diagrams and 3D models, students may over-rely on traditional medium and 2D representation. And by the way, different points of view on the same model provided fruitful for students' advancement. So, also, I have different, so my graduate student, Diana Rozensky, she worked, and there are different findings about this kind of learning. So it was a great variation between students in the way they interact with 3D models when solving special geometry questions. It takes time for students to get used to a 3D medium, overcoming dependence on 2D. And, but in for all the students, breakthroughs in the solutions, and we played not only with this task, but also with other tasks in the solution are related to movement, rotation, change of perspective, or understanding of the student's other point of view, literally. Second experiment is, I call it constructing enactive argumentation, gesture, action, and medium. So these are here, this is the question that we are asking our students. So first of all, your team have to construct a three-dimensional model of the following geometrical solid using a construction kit. The solid has the following properties. All the faces are congruent equilateral triangles. The same number of edges converge at each vertex. This is the kit, okay? The length of these rods are approximately 1 meter. Sometimes we are giving them like ½ meter, and these are connectors. And they have this illustration, so they know we are not saying how many vertices are coming, how many edges are coming from each vertex, but we are giving them an illustration so they can see. Then, when they constructed this, they receive another. The polyhedron you've constructed is called a tetrahedron. Construct a similar polyhedron whose edges are 2 times larger than the original one. You can use the image below for construction. So, and we are prompting them to build not just, to build something like this, okay, in this shape. Because, but as you can see, these are opaque shapes, not transparent. And what they are building is, and this is also 2-dimensional representation, of course, 2-dimensional diagram, and what they are building is 3-dimensional, okay? And then we ask some questions. One of the questions is comparing the volumes of the large and small tetrahedron that you built. How many times the volume of the large tetrahedron is greater? And then we are asking them to explain their answer. And then several small tetrahedra compose another question. Several small tetrahedra compose the large tetrahedron. Can you describe a 3-dimensional shape between them? So you can see this shape, this void, yes, between these 4 initial tetrahedrons. Can you construct it? So, so you can see that these are younger kids. They are in 8th grade, okay? And so they are constructing this, and now they are doing this with approximately, the rods are ½ meter long. Okay? And you can see several stages of construction. This one, I think that this is not just cute. So boy is putting this on his head, yeah? So it's not, it actually, when we tried this with 20 or something groups, 20-something groups, always someone is entering inside the shape. Always, always, and sometimes much more of this. So this one is much smaller, but so I think that this is some primordial, that when we construct some shape, we have to inhabit it. Inhabit, sorry. Okay, so, and you can see these explanations, and this is the shape, so they cannot see. I added these red lines for you. But they cannot see this. It's not highlighted for the students. They have to understand what is happening there. And trust me, this is not an easy question. Because I tried this also with pre-service teachers, like brilliant mathematics students from Hebrew University, one of the top mathematics departments in the world, and also with experienced teachers. And the answer is not coming immediately. So the people are not perceiving octahedron there. Okay, so I will talk what is happening here. So first of all, they constructed the first structure, and boy put this. And the girl, she's trying to explain why this is called tetrahedron, because in Hebrew we also have special word for this. Arbaon, arba is 4, so, and she is gesturing the faces. And so once one group had constructed the first small pyramid, Yali, his name put at head, and she's used Yali as a stand and gestured on him that polyhedron is called Arbaon. The palms of your hands present the polyhedron's faces. By the way, it is interesting because her gestures are palms. She's not pointing. She's using palms because she's speaking about, and this is consistent. She's speaking about faces. Then you can see she is switching to movement of a forearm. So she is trying to demonstrate some kind of play for her peers. So here they constructed the bigger model, as you can see, and they started to reconsider the volume. It took the students approximately 11 minutes of collaborative work to construct a large model. They easily recognized 4 small tetrahedra, and they said 3 at the base and 1 at the top. And they were not sure about the shape of 3-dimensional hollow. And some of them, okay, so they are arguing here and trying to understand what is happening. But can you see the sheets of paper? That was, I was taken by surprise because it was a pile of sheets of paper that was just happened to be in the classroom. And one of them just realized, oh, we can do this. And so I'll just read this. Tami, Nami, and Gali suggested that the hollow is also shaped as tetrahedron. And Yali disagreed and offered to count the faces of the empty space. He rotated the large model. Actually, this is very good strategy, hoping to render it more familiar, yet that action proved unhelpful. Kami remonstrated, you just can't see this tetrahedron. To support her claim, she grabbed 2 sheets of paper lying on the desk and applied them successfully as a polyhedron's faces, expecting this to total at 4. But it was not 4 because there are 8. So, but immediately Yali recognized the potential of this method, and he asked them, each of them, to take 2 sheets of papers and apply at the places where the faces are. So immediately Yali appropriated Tami's strategy just to disprove her. Summoning more paper sheets and distributing them over more group members, he marshaled an octopus of hands to simultaneously cover all the polyhedron's faces. The introduction of these auxiliary objects helped students to solidify the shape, count the faces, and eventually write the following definition. By the way, this is very good, I think, for 8th grade students. The polyhedron, so they use the correct word in Hebrew, between 4 triangular pyramids, has 8 identical faces. Each face is an equilateral triangle. Okay, so they continued the exploration, but here I will focus only on this small episode. So, first of all, we know that the activity of defining is not coming naturally to students. But here, the need to define the object was raised naturally from the idea to compute the volume as sum of volumes. Students' solution was totally collaborative. And we can see it was adoption and adaptation of each other's ideas. They use collaborative actions and gestures. So for instance, it was impossible for one of them to cover all 8 faces, but then they just regrouped and did this. The solution involved different types of gestures, pointing, formative and iconic gestures, actions, and use of visible media. The solution involved the transition from iconic visualization to non-iconic visualization, was carried out by introducing tangible auxiliary elements, paper sheets in the form of polyhedron faces. So I'm using here the words iconic and non-iconic visualization. This is from the work of Duval and from the work of Metalal and Balashov. So iconic visualization, when they use images, and non-iconic visualization, it's verbal definition. Okay, so and it was possible to by introduction of auxiliary element which separated this octahedron from the rest of the shape. The object was defined by stating the property of the faces and by enumerating them. This is just okay. Then I will show again a different experiment, third experiment, which is very similar, but yet we are using another shape, and then we can discuss them together, okay? So in different experiment, a group of students were given the following instruction. Your team has to construct two three-dimensional models, one large and one small, of geometric solid, a polyhedron. The polyhedron has the following properties. All the faces are congruent equilateral triangles, and the same number of edges can converge at each vertex. So this is the same, but the structure, the diagram is different. So instead of tetrahedron, they are supposed to construct icosahedron, 20 faces, yes? And also, they have two sets. They have to construct one large, like 1 meter long rod, and very small handheld model. I think it's 10 centimeters long, something like this. And the questions which we asked after they constructed these two models are: how many edges does the polyhedron you built have? How did you calculate that? If the polyhedron, this is interesting question, by the way, if the polyhedron was half full with water, what would be the shape of the surface of the water? Like cross section. When the polyhedron is on a triangular base, and what about when the polyhedron is tilted onto a single vertex? Okay, so this is two different configurations. This configuration and this configuration. Okay, and we also asked different questions, but I will focus on these two. I will, okay, here I should add additional theoretical consideration. So in very good book of Herbst and colleagues, they are talking about mathematical modeling of geometric figures that they should take into account four distinct perceptual systems of the figure. First, physical navigation of macro space, objects more than 50 times the size of individual. B, capturing an object in mesospace, half to 50 times. As constructions of small objects in microspace, less than half times than the individual. And finally, description and manipulation of small objects in microspace. I have to point out that in general, in normal classes of geometry, what we are doing mostly is descriptions and manipulations of small objects in microspace. That's it. Once in a while, we also construct small objects in microspace. For instance, we draw some pictures. But still, these are not material objects. Forget about physical navigation of microspace. For instance, it's very rare if we have, for instance, mathematical trip and we have to go somewhere and to draw with our movement some shape on the map, or to navigate as a learning activity, or capture an object in mesospace. Here, what is happening is exactly this: capturing object in mesospace, but also playing with something very small. So here, this activity is playing with two perceptual systems of the figure. One, human size, even more, like almost 2 times bigger than human size, as you will see, and something in microspace. Okay. So here I display this. So now I'm focusing on what is happening after they create it. Because in the previous example, I showed how they constructed and how they introduced them. So here, as you can see, they have this small model and it's lying on a face. And they started to discuss this. And now they're trying to discuss this resting on a vertex. And one of the students, okay, Gray holds a model on its vertex and start counting 1, 2, 3, 4, 5, touches an upper vertex, touches two additional vertices, and black it's by the color of their t-shirts, okay? So it's gray, black, yellow, gray, and I think orange will come at some point, and also blue. Okay, so that's their t-shirts. How many vertices? We already counted. It's a number of joints. But okay, it's a number of joints, but you have to count the joints, yes? 12 times 5, 60. How it can be 12 times 5? How it can be 60? Because like they have this. And gray tries to take a model from yellow. Vertices. Okay, it's 12. Put it like this. So he's trying to orient the model on vertex because he has some know-how. But yellow is just taking this from him. I know what I'm doing, and she's just counting in different way. There are 12, and this episode ends, as you can see, that yellow, the girl, she answered it correctly, it is 12, but gray, he failed to explain his method, okay? But then, what is happening? Okay, the small model is the focus of students' attention. Small model, what it affords to students. So if we are talking about like in language of affordances, in Gibsonian language, small model affords the student to group around it. So they are sitting around it on the floor to simultaneously grasp most of its features, holding the whole. Okay, this is structure of rotation of Mason. All the vertices are in the hand reach, enabling students to discern them by touching. So they try to touch the vertices. The counting was conducted in two different ways. By orienting the model in a particular way, Gray recognized a relationship between several groups of vertices of the icosahedron. Yellow was also successful in her attempt to count the vertices, which is separated into two groups of 2 and 10, like 2 which were close to her, and then she was able to count others. Okay, but now what is happening? Now they have to count edges, and this is much difficult for them. How many edges are there, saying yellow? Okay, that's tricky because they are shared. I'll put a finger on the edge. Just count the sticks. And then yellow, she's saying, I will go to the big one, to the large scale model. And another one saying, the big one is just nicer. So they have two models, one of them like this and one of them bigger. And part of the group, they're saying, well, we are going to the big one. And you can say why. Now you can see that this model affords different features. So it is this model of the same mathematical object, but the affordances are totally different. For instance, you can go inside. So yellow is saying there are 5 from each vertex. This is, by the way, very important that she knows this feature. 1 should be subtracted. I don't know why she's saying that. Then there are 4. 2 should be subtracted here. It's 3. It does not work this way. And she, at some point, she sits inside the model and she's frustrated. I can't count this. And she tried to say something, okay, but then Gray finally have his moment of glory. And he's saying, I'm tilting it. And he starts to tilt the model. She's trying to count, and this is disrupting her. But what is happening is this. So when the model is oriented on its vertex, then the vertices are discerned in 3 different groups. And they call this group base, and belt, connecting belt. And then, so Gray said, to make it like this, it will be easier to count like this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then yellow, she picks his idea and saying, okay, 1, 2, 3, 4. And then she counts what is up, base down, and lower base and upper base. And then she counts this. And she arrived at the correct, answer 30. So I will summarize, and then we go to discussion. The focus shifted from a small to large model. So it was a shift from different focuses. Large model affords the students to discern details visually. It enables new action to get insight and new perspective from the inside. Not all the edges are in the hand reach from outside, but not all the edges are visible from the inside. Both students perceived useful properties, 5 edges from each vertex, 3 edges forming a face, but one of the physical orientations did not allow reasoning based on perceived properties, and one of them did. Physical action shifted the focus and structures of attention. So, what I'm saying, I will skip this. I'm saying that models of different scales lended students different affordances for inquiry. Each model served a physical attractor with different affordances for and constraints on the action. Accordingly, students recognize themselves and their exploration in accordance with the affordances and constraints. The affordance of a large model to be explored from the inside were realized. Also in all the cases in our possession. As I said, they always go inside the model. Students constructed the models, moved between the models, and incorporated its actions and features they noticed as a result of action in their solutions. So their solutions, mathematical solutions, were based on their actions. So I guess that I will open discussion now and say that these case studies, they highlight the pedagogical potential of embodied approach in spatial geometry instruction, and that different activities enable students to ground conceptions of the geometric figures simultaneously in the last case as objects in mesospace and microspace, providing more opportunities for possible shifts in focus and structures of attention. And in general notice, I think that we should continue to study these different environments and different affordances which they present with our students, and that to do geometry, so I think ultimately my goal is to build theoretical and practical foundations for a different curriculum for spatial geometry at least, because some of the students now, they are, as I said, tactily and kinesthetically left blind, and that is why they cannot participate in lessons, and they cannot use their facilities developed by evolution, their perception and their action, and exploit all the possibilities of their body for their thinking. And so here I stop and I'm open for discussion.